Okay, this is board problem 32. This is for lesson 6.2-3, and I'll get to that in just a second. So if you choose a card at random from a well-shuffled deck of 52 cards, what's the probability that the card chosen is not a heart? Okay, going to use the complement rule on this, you guys. The probability that you choose a heart is 1/4 or 25%. So the complement rule to be not a heart would be 1 minus 25%, which is choice C. Okay, complement rules are the ticket. You'll find out a lot on these, you guys. All right, 6.2-3, independence and the multiplication rule. Okay, multiplication rule for independent events says if A and B are independent of each other, meaning that the knowledge of one event does not change the knowledge of the other, or does not change the other, then the probability of both events happening is you just multiply them, you guys. So as long as they're independent, then if you're doing them at the same time, you just multiply the results, the probability of each multiplied. So independent versus dependent. This is example 612 on page 551 and 52. Because a coin has no memory and most coin tossers cannot influence the fall of a coin, it is safe to assume that the successive coin tosses are independent of each other. For a balanced coin, this means that after we see the outcomes of the first toss, we still assign the probability to 1/2 to the second toss as well, and 1/2 to the third toss, and 1/2 to the fourth toss. The first and second and third toss has no influence on the successive tosses after that. So that's why it's independent. They're each independent of each other. On the other hand, the cards if you pull some colors out of the cards of a deck, they're not independent. So for example, a standard 52 card deck contains 26 red and 26 black. And so if you pull the first card and you recognize that it's a red card, well, that's 26 out of 52. But if you leave that card out, you guys, and we talked about this yesterday, that if you leave that out, then the next card you're going to pull out, there's only 25 red cards in there and 51 cards left, so it would be 25 out of 51. Okay, your book is fond of changing these to decimals. I like fractions, but that's okay. 50%, this is 49%, so they got that out of 25 divided by 51. Okay, so you see the difference between this one's independent, the coins are independent of each other, whereas the cards pulling are dependent of each other as long as you leave it out. Okay, here's another one. If a doctor measures your blood pressure twice, it's reasonable to assume that the two results are independent because the first result does not influence the instruments that makes the second reading. So they are totally independent of each other. But if you take an IQ test or other kind of mental test twice in succession, the two test scores are not independent because you learn from the first test and the learning occurs has influence on the second test. So it's not independent of each other. Okay, so when an independence is a part of the probability model, then you can do the multiplication rule that I just showed you. Okay, so here's an example. The Atlantic Telephone Company, and this is kind of weird. Example 614, page 353. Okay, the first successful transatlantic telephone cable was laid in 1866. The first telephone cable across the Atlantic did not appear until 1956. The barrier was designing repeaters, which were amplifiers needed to boost the signal that could operate for years on the sea bottom. This first cable had 52 repeaters. The copper cable, laid in 1983 and retired in 1994, sorry, 11 years later, had 662 repeaters. The first fiber optic cable was laid in 1988 and had 109 repeaters. There are now more than 400,000 miles of undersea cables, with more being laid every year for the flood of the internet traffic. Well, I suspect that the satellites are slowing it down, but they're still doing that. So repeaters in undersea cables must be very reliable. To see why, suppose that each repeater had a probability of 0.999 of functioning without failure for 25 years. Sounds pretty good, huh? Repeaters fail independently of each other. This assumption means that there are no common causes such as earthquakes that would affect several repeaters at once. So denote A sub I, which is the event of the ith repeater operates successfully for 25 years. Okay, so the probability that two repeaters both last 25 years, since they're independent of each other, then we just multiply the probabilities. So we do 0.999 times 0.999. So the probability that two repeaters last for 25 years is 99.8%. Okay, for a cable with 10 repeaters, the probability of no failures in 25 years is basically 0.999 to the 10th power, because you keep multiplying them all together and you get 99% on that. Still pretty good. Okay, but cables with 2 or more repeaters would be quite reliable. Unfortunately, the last copper transatlantic cable had 662 repeaters. So if you do 0.999 to the 662 power, that's just a little over 50%, you guys, 51.6%. So this cable will fail to reach its 25-year design life about half the time, a little over 50%, if each repeater is 99.9% reliable over that period. So the multiplication rule for probabilities show that repeaters must be much more reliable than 99.9%. Whoops. Sorry, let me get that back down there. Okay, let's see. So here's some AIDS testing designs. Okay, and this is example 615 on page 354. Screening large numbers of blood samples for HIV, the virus that causes AIDS, uses an enzyme I can't say that, EIA test that detects sorry, antibodies to the virus. Samples that test positive are retested using a more accurate Western blots test. Applied to people who have no HIV antibodies, the EIA has a probability of about 0.006 of producing a false positive. That means they got tested positive when they are not positive. So if the 140 employees of a medical clinic are tested and all 140 are free of HIV antibodies, what's the probability that at least one false positive will occur? Okay, so it's reasonable to assume as a part of the probability model that the test results for the different individuals are independent. The probability that the test is positive for a single person is 0.006. So the probability of a negative result is the complement, 1 minus that, so it's 0.994 by the complement rule. The probability of at least one false positive among the 140 tested is therefore, it's going to be that 1 minus 0.994 to the 140th, because there's 140 right there, and you get about 56.9%. So out of those 140, there's 56.9%, almost 57%, that someone's going to test false positive on that. Okay, that's it for that one. There's one more fall on this.